what we were doing. So let's recap. Last session, let's recap the essence of exercise 3F. Okay, so 3F was about the graph of an exponential. You don't have to write this in, this is just me recapping for now. So graph of exponential. There were two key things that when you're sketching an exponential graph, which I'm going to draw one up here for you to see. Here's an exponential graph. So as an example, let's just call it 2 to the power of x. Okay, that was the first example I gave to you. There are two key features. Every time you sketch a exponential graph, there are two things you must label. What are those two things? Name me one. Hands up. What are the two things? Go back to your notes. Violet? The growth, yes, that is correct. It is growth versus decay, which we'll talk about in the next bit. But there's two key things you must label. What is it? The y-intercept. Now, what's special about the y-intercept again? What's so special about the y-intercept? Yes?
It's always at y equals 1.
Very good. Unless you move this graph left or right, then it will change it. But otherwise, anything to the power of 0 is 1. So even if I change that to 3 to the x or 4 to the x, they will all cross at 0, 1. Because anything to the power of 0, by law number 6, it is going to equal to 1. So 0, 1 is a key feature that you must label. What's the second one? Andrea? Asymptote. Asymptote. What does the asymptote mean again? Hands up. What does it mean? Right, Andrea?
The graph approaches infinitely close to a value.
Very good. So what we realize is if it was 2 to the x, as you move to the right, what's happening to the pattern? What's happening if I keep moving to the right? Every point was doing what? It was growing, but if it's base 2, what does it do? Doubles. Okay, so every time you go to the right, if it's base 2, it's doubling. But what's interesting is that if you go the other way, instead of doubling, it is halving. But that was the problem, or the thing that was interesting about this graph, is that you can keep halving numbers infinitely. That's why it never touches 0. There's never half of a number that actually equals to 0. And that line will infinitely get close to the x-axis. So we call that an asymptote because we can see it's reaching a particular value, which in this case is when y is equal to 0. It's reaching there, but it won't ever actually equal to it. That is called an asymptote. That's a horizontal asymptote. You must label that. As y equals 0 is to show there is an equation that it's approaching. Later on in year 11, you start moving the graph around so that there will be limits to where it reaches. It doesn't always have to reach 0. It can reach 1, it can reach 2, and then you can change that. Okay? So those are your two key things. And then the last part of 3F that I was trying to teach, and I confused you all by giving you too many negatives there, it was just two things I wanted to show, which was growth versus decay. Now growth, which is the one that I gave to you, 2 to the x, because as you move to the right, the graph is increasing. So as time increases, your graph also increases, which there's a lot of applications we can model where something grows over time. Versus if I want to make it a decay, in your notes, how do I make it a decay? Yes, Violet? Yeah. How do I make it look like the equation? What do I change? Very good. The negative on the x. And then because I assumed that, by putting extra negatives, we'll show you the different things that you could do to the graph. It confused you. You don't need to know the other two. I had one where I had negative in front. I had negative on both. But all you need to know for 3F was this. The understanding of what the shape looks like, how it approached, or how it became this, because we were doubling. But when you go to the negative side, it then halves. So if it's 3, it's tripling, and then going to the left will be 130, right? And then there's growth versus decay. And the only difference is when you put a negative on the x, all the positive x now turns into a negative x. That's why it flips across. Okay, so what used to be a positive 1 now is negative 1. That's why what it was on this side now flips over to that side. That's why the graph decays. Okay, so that's the logic. Now that you got that graph and that visual, that's what they wanted you to understand. Now, we're doing an application. So how does the application work? Let's do this example. So now go to your sheet. After 3F, we had the next 2 pages. 2 examples. I'm going to show you where indices comes in and why we learnt the algebra and the logarithms so you can solve a problem like this. Okay, so let's have a look. Example 3. If you went to your last session, I still got, I think, 3 spares here. Was anyone not here last session? Anyone else who wasn't here last session? I've got 2 left. All right. Here we go. Example 3. Paris has a painting that is valued at $100,000. So Paris has a painting valued at $100,000 and it is expected to increase. So when you see the word increase, you're thinking it's going to grow. But there's a lot of graphs that can show growth. You know, you've got linear graph. That's growth. Goes up as well. But how do you know this is going to be exponential? I'll show you. It says it increases by a value of 10% per annum. What does annum mean? It's a year. Okay, so for every year, it increases by 10%. Now, this is the key part. So when A, it says write an exponential rule to model the growth, where A is the final value and T is the time in years. Ignore that bit for now. Let's just recheck our percentage knowledge. Okay, so from year 7 to 9, you would have learned percentages. Now let's think about it. How do you calculate the value of a painting after 1 year if you know it increases? So $100,000 increases by 10%. How do you work out something that increases by 10%? So let's say if I change that $100,000 to $10, what would it be if I increased it by 10%? Okay, so what did you do there? So you're right. How did you get 1? Okay, so 10% of 10, which is equivalent to saying of means times, and 10% means 10 out of 100. So 10 out of 100 times 10. Now we know we can simplify this fraction here. 10 over 100 is the same as 1 out of 10. So really you're saying what's 1/10 times 10, which is the answer of 1. Okay? But what's the actual answer? So if I had $10 and after 1 year it increases by 10%, how much do I have now? 11. So how did you get 11? You added it. Now this is the key part. So you said $10 is what I started off with, and then you added on the $1, which is from the getting 10% of 10. Now if you think about it, this is the result of 10% of 10. Well, what's $10 as a percentage of itself? 100%, right? So this is really just saying I've got 100% of 10. Now, if you added them together, you just think in terms of fractions and the pieces. I've got 100% of 10 plus another 10% of 10. If you visualize that, what I'm really saying is if this is 100%, if this entire thing is 100%, I'm adding another 10% on top. You see that? I'm just adding on an extra 10%. So overall, I should have 110% of 10. Does that make sense? Okay, now this is key. See, the 10 was what I started off with. So I'm going to highlight it. Of means times. 110% means 110 over 100. But if I simplify that fraction, what does it become? 11 on 10, which if you divide it as a decimal, 1.1. This is what I want you to understand. When you increase a value by 10%, what you're really doing is you're saying it's the same as multiplying by 1.1. Because that's what you're doing. You're taking the original value, which is where the 1 comes from. The 0.1 is that extra 10%. That's why 1.1 represents an extra 10% of its original, if you times it. Okay? So now let's answer the question. The question, if we were to model it, let's have a look at the pattern. And you'll see where the modeling comes from and why exponentials comes in. Yeah? Here we go. We start off with $100,000 rather than $10. Now, in the first year, or 0 year, as soon as you borrowed the money, as soon as you got the painting, it's worth $100,000. That's the beginning. So that's the value. After 1 year, Okay, so that's 365 days. After 1 year, it should increase by 10%. So 100,000, if I want to increase it by 10%, what do? Times by 1.1. Now you can do that on a calculator or you can do it mathematically, but what is 100,000 times by 1.1? Or you can think of 10% of 100,000 and then add on top. What would that give you? 110,000. So I now got $110,000. That's after 1 year, right? Then in the second year, what would you be doing then? So after another 365 days, what would the value be? Because it increases by 10%. What would you do? Beautiful. So you would then say, whatever this amount is, this amount over here, you would say 110,000 times by 1.1. Agreed? Okay, so that's what you would have done. Now, let's work out what that is. I'm going to use my calculator. Actually, I'll do this one. This is quicker. So I got 110,000 times by 1.1. I get 121,000. Now, this is where it's key. This is where you'll see the pattern of where exponentials comes in. See, 110,000 times 1.1, if you realize 110,000 was the result of getting this. See that? 110,000 was this. It's 100,000 times 1.1 to get that answer. So instead of writing 110,000, what I can do is I can resubstitute this 110,000 by that statement. Yeah, I'll replace that because this is 110,000. Now, if that is 110,000, what you get now is you get 100,000 times 1.1, because remember, this is 110, times, which I'll do color coding, times 1.1, because that's what you were saying here. You said times by 1.1, this is your 110. Now, what's nice about this is there's a pattern. Do you notice that you're timesing 100,000 is what you started off with? That's your first 10% in the first year. In the second year, you're doing another 10%. So that means it's 1.1 times 1.1, which we know we can simplify by indices. What's 1.1 times 1.1? That's right. So this now becomes 100,000 times by 1.1 squared. Now this is nice because had you not replaced that, every time you want to find the next year, you need this number. And you have to put it down here, then you times it by 1.1. Then you get this number, and then you have to put it down. This is called recursive, right? It takes too long, because if I ask you what happens at the 99th year, you can't figure it out. That's why you need a model. Now, if you see this, there's a pattern. Second year is squared. First year is power of 1. 0 years to the power of 0. So that means in the third year, if you had to write it, it'd be 100,000 is what you started off with, times by, and remember, this is going to be whatever this is, so 121,000 times by an extra 1.1. So it ends up being 1.1 cubed. So the third year becomes cubed. Fourth year becomes to the power 4. Fifth year becomes to the power 5. So if I asked you by 99, you just need to know how much you had to begin with, and it's divided 10% to the power of 99. And you can calculate that. So if I asked you to model it now, answering part A, we can then say, well, the model is the amount is equal to how much you started off with, which was 100,000, times by 1.1, which is the 10%er, to the power of, well, it depends on how many years you want it to be left for. And that's what the question was asking, saying leave it as A is the amount that you'll get. T is the amount of years. So if we put 0, we get 100,000. Put 1, we get 110. Put 2, get 121,000. Does that make sense? Okay, so you can see now how I've changed a 10%er to use indices, and that repetition, that 1.1 to the power of t, is a graph. Remember, we said the base had to be greater than 1, and you get this exponential graph. So if you put it on Desmos, you can see, where is it again? Desmos, here we go. And I'll take that off. If I put y equals 1.1 to the power of x, that is an exponential graph. That's what you have. The only difference is you're not starting off at $1. You're starting off at 100,000 dollars. So if I zoom out, you can see this is what the graph would look like. Well, I have to adjust the x-axis and all that. But that's an exponential graph. Okay? This is where you're solving now. So all the algebra that you've been doing, you can now solve this type of equation. So let's go. Let's solve some things. Question B. So we've modeled it. Question B says, how much will his painting be worth after 4 years? So I've got a table here and you could work it out, but now we've got a rule we can work out after 4 years. T equals 4. So your answer must be A is equal to how much you started off with, 100,000. You got the answer? Okay. Tell me, because I haven't typed on the calculator yet. 100,000 times 1.1 to the power 4, which is? 146,410. All right, let's check that. So I'm going to use my CAS. Let's check. 100,000 times 1.1 to the power of 4. And you're correct. Okay, so that is the amount it's increased by. So after 4 years, starting off 100,000, it's not increasing at a constant rate. So it can't be linear because you keep doing 10% of the amount. It's going to keep changing. This is how your superannuation works. You know, so you put in the money, it starts off slow, but over time, it grows. So one of the things about financial advice is that the earlier you start investing, time is your best asset. Time is what people can't buy back. The earlier you invest with that compounding interest is in your favor. That's why even if you start off with very low money, but if you just put it in, your time, the earlier you put it in, over time, you'll always beat someone who put in, say, 500,000 to begin with. They won't grow as fast as you. You will grow over time much bigger because the compounding depends on time, which is why in 3H it becomes really interesting because E talks about what if you can compound infinitely? What if something compounds so infinite every single instant? What would that be? What does that represent? That's why 3H is interesting. Yeah? Let's do. So we've done that. That's applying. Now let's try to solve. So how do we solve? Let's look at C. It says, how long will it take for his painting to be worth $500,000? So he bought a painting. It's $100,000. And he's thinking, well, I want $500,000. Then I'll sell it, right? So how long will he have to hold it for? We can calculate this. We want A to be $500,000, right? That's what we want before he decides to sell it or something like that. He just wants to know how long he has to hold on to this painting for. Now we calculated that the formula was A is you started off with $100,000, 10% of that for the number of years that he's going to hold on to the painting for. Now if the amount is going to be $500,000, the question is, what's the time? So here we go. We've got an equation to solve now. Using what you know. Let's see how much you've learned from logarithms here. How do I solve this? I'm trying to find t, which is the power. Jada. Beautiful. This is time, so it's Sam dot, which is opposite of bud mass. Divide both sides by 100,000 first. Divide this by 100,000. That cancels out. 500,000 divided by 100,000 is now 5 is equal to 1.1 to the power t. And this is what we've been training to do. We've been trying to get rid of exponents. So 1.1 to the power t, how do I get rid of 1.1? Log it. Now, log is the inverse of exponent. What base should I be doing? Okay, so if you have a senior calculator, you can do 1.1. If you don't have a senior calculator, you will do log base 10 or log base e. Right, I'm going to show you both methods so you can see. So if you did log 1.1, conveniently, these two will cancel out. T will equal to log of 1.1 of 5. Right? That is what we've been training to do. Now, if you had a senior calculator, yes, you can type that in. You can do log of 1.1 of 5. But if you didn't, then this is the other key step. At 5 equals to 1.1 to the power of t, you could have done log base 10 of 5, log base 10 of 1.1, but you have to do something, little extra something to rearrange it. What do you have to do? Not sure? It is the change of base formula, and that comes from doing something here. There's one step. There's one rule that year 12s that I keep reminding them that the one log rule, what do you do? What can you do to that power?
Oh, you can bring it to the front.
And what rule is that? Rule number three. Rule number three says you can bring it down. So if I bring it down, you now have this. You have log 10 of 5 on the left, t times log 10 of 1.1. And then now we can find t, because we don't need the times log 10 of 1.1, whatever that is, right? So what do you do now? Oh, yeah?
Can you only bring the two when there's a log?
Yes, because that's log rule number 3. That's the only time you can do that. What do you do now? So I want to find t. How do I get rid of this? What do you do? Yes? Yeah, and that's the change of base formula that Sanvu was saying before. See, if you divide both sides by log base 10 of 1.1, these cancel out, and that literally is the change of base formula. T is equal to log 10 of 5 over log 10 of 1.1. This is the same as this. That's your change of base formula. That's where it comes from. But the first thing was, that was from rule number 3. You have to understand rule number 3 to be able to get to change of base. Yeah? So now if I try it on the calculator, I'll show you that they're both exactly the same. Here we go. If you have the senior calculator, control 10 to the power of x, because that's where log is. And now I can type in 1.1 of 5. Takes him about 16.88 years. If he holds on to that painting, he will get half a meal. Or, if you didn't have a senior calculator, you could have done log base 10 of 5 over log base 10 of 1.1, and you still get the exact same answer. So it doesn't matter which calculator you get, but just knowing how to work with logs and exponentials the way you've been doing, that solves the problem. So now you can think about, well, yeah, if something increases as a percentage, which most things financial does, it works with percentages. This is how you can calculate. You can think about investing in a home. You buy a house, it's X amount. How long do you have to hold it? And over the years, as it grows, what kind of percentage do you need to get a certain value you want? You can work it out. It's possible to do. Yeah, so that's 16.8 years, but we haven't answered the question properly yet. The question asks you, how long will it take for this painting to be worth 500,000? Round to the nearest year. What's your nearest year? 17. Now, even if it was 16.2, you don't round it down to 16. Why? Why don't you round it down to 16? Very good, because the point was he wants 500,000. If you round it down to 16, but it was 16.2, he's not going to get his 500,000. So the closest year to get 500,000 is 17 years. Okay, so this is where at a year 12 level you have to think about the application. When do you round up, when do you round down? Okay, so in this case, yes, it's easier because it's 16.88. But yes, you would then say, therefore, it takes 17 years to reach. Sorry, I should write the answer. That's 16.88 something. So 17 years to reach 500K. Does that make sense? Okay, so that's why we've been training with the algebra, and then this is the application. The key part was the percentages. The repetition of timesing by 1 on 10 or 1.1 is what I want you to understand. Have a go with the second one. I'm going to pause the video. Second one is a decay problem. So growth was you added on. Well, how do you solve if it's losing now? So if I'm losing by 15%, what changes? I want you to think about it. Have a go. And that's exercise 3G. Okay, that's exercise 3G. For example 4, you should have got 400,000 to start off with, times by 0.85, because it's 1 minus 0.15 to the power of t. And then here would just be A is equal to 2, 400,000, 0.85 to the power of 6, 400,000 times 0.85 to the power of 6. You get 150,859, $158,509.81.
Why did you say yes?
I don't know. All right, see, how long will it take for the share portfolio to be half its value? So we need 8 equal to 200,000.
Wait, I just dropped one of these. I left it in your pocket.
All right, team. That's the answers. Should have been about 150,859. Yeah, no, I just thought I'd do that. And then this one should be about 4.2 years, or ran into the nearest year would be 5 years. If you got that, that's exercise 3G. Okay, that's 3G. Growth versus decay.